Hello everyone, my name is Anirban Sinha. I am a PhD student in the Department of Mechanical Engineering at the Stony Brook University. I'll be presenting the paper titled on Screw Linear Interpolation for Point-to-Point Path Planning. The co-authors of this paper are Mr. Anik Sarkar and Professor Nilanjan Chakraborty. The proposed work in the paper is partnering to development of a task-space-based planner using screw linear interpolation such that some common robotic tasks with path constraints can be maintained without even explicitly modeling the constraints. Planning and control of motion of a robot manipulator to go from an initial to a goal configuration is a fundamental problem in robotics. Additionally, during motion, different constraints on the end effector may have to be satisfied. For example, consider the dual-handed manipulation task shown in the figure on the right, where the robot has to hold a tray with a glass of liquid with both hands and move it from the initial to the goal pose. To accomplish the task successfully, the robot has to compute a path such that the relative pose between the end effectors as well as the orientation of the tray do not change along the entire path. Joint space-based planning approaches are widely used class of motion planning techniques. However, Berenson et al. And Stillman, along with others, identified the complexity of the problem of maintaining task constraints using joint space-based planning schemes. On the other hand, many task space-based planning approaches consider no change in orientation of the end effector along the path, so that mere interpolation in R3 can be used to trace a path in task space. In order to take into account both change in positions and orientation along the path, some papers consider variants of AC3 interpolation methods. The goal of this paper is to study motion planning problems with end effector constraints that have to be satisfied during the motion. We show that using screw linear interpolation method to generate task-based path naturally satisfies some common task constraints. Here, I quickly go over some mathematical preliminaries to understand the content of the paper. First, I'll describe quaternion. A quaternion is a hypercomplex number represented as capital Q is equal to Q1i plus Q2j plus Q3k plus Q0, where I, j, k are imaginary numbers. Q0 is the real scalar part, and Q1, Q2, Q3 forms the imaginary vector part of a quaternion. A unit quaternion has its norm equals to 1 and is used to represent rotations. Using quaternion multiplication, we can compute the composition of rotations. Given two quaternions P and Q, their quaternion product can be obtained by the equation given here. A dual quaternion, capital A, consists of two quaternions, the real part capital P and the dual part capital Q. Dual quaternions are useful in representing rigid body poses. Suppose the orientation of a rigid body is represented by a quaternion A subscript R and the position of the rigid body is T. Then the pose of the rigid body can be represented by a dual quaternion as capital A is equal to AR plus epsilon divided by 2 times quaternion product between T and AR. Screw linear interpolation is a method to compute a curve in AC3 by interpolating between two given poses. It is the analog of the shortest path motion in R3 for motion in AC3. By varying an interpolation parameter tau between 0 and 1, any intermediate configuration C tau between A and B can be computed using the equation shown here. When tau is equals to 0, C tau equals to A and C tau equals to B when tau is equal to 1. In the figure above, we have shown the frames on the end effector path computed for door handle rotating task using screw linear interpolation based task space interpolation. In this slide, we formally define the path planning problem with task constraints. Given the initial and goal end effector poses as G0 and GD, we want to find a sequence of joint angle vectors theta i's such that Forward kinematics of the final joint angle vector provides the desired end effector pose. Path constraints are satisfied. Collision constraints are satisfied. Joint space goals are satisfied. Please note that in this paper we are interested in dealing with path constraints only imposed by the task. Here, I will provide the intuition of the working mechanism of the proposed planner. Suppose the gray oval area in the left represents the task space of a manipulator, and the gray oval on the right represents the joint space of the same manipulator. The initial and goal end effector poses of the task space are given by the red and green circles respectively, and the corresponding initial joint angle is given by the red circle in the joint space region. Next, using screw linear interpolation, we compute an intermediate task space pose as the blue circle here. And applying resolved rate motion control technique, we get the corresponding joint space angle vector, which is the blue circle in C space region. Then we solve forward kinematics to get the actual end effector pose in task space as represented by the yellow circle. This completes one iteration of the proposed planning scheme. Next, we repeat the same steps between the yellow circle and the green circle lying in the task space and continue until goal is reached. Here is the discrete time kinematic state update model of the proposed planner. At any time instant t, given the end effector pose gamma t and the corresponding joint configuration theta t, using screw linear interpolation, we first compute gamma t plus h. Then, knowing gamma t plus h, and theta t, the joint angle vector theta t plus h is computed. The expression of capital B matrix is given in the second equation. Here, we will again consider the door handle rotation example to compare the path computed by the proposed planner using screw linear interpolation and another planner which considers interpolation of position and orientation independently. As can be seen in the left figure that our proposed planner computed the path while maintaining the rigid constraint imposed by the door handle. On the right-hand side figure, we have compared the two paths computed by the proposed planner and the other planner. As can be seen that the path computed by the proposed planner maintained the circular path while the path computed by the other planner did not maintain the circular arc, and hence as was unable to maintain the task constraints. In the table here, we have presented the key subgroups of AC3 and examples of the types of motion constraints they encode. These include the subgroup of pure translations as presented in the first row, pure rotations in the second row, motion in a plane in the third row, set of all motions that can be generated by a cylindrical joint in the fourth row, and motions that include screwing and unscrewing operations in the fifth row. Please note that when we say that the motion is constrained to be in a subgroup, it implies that the screw corresponding to the motion is in the subgroup. It does not imply that the end effector pose has to be in the subgroup. For example, in door handle rotating tasks, the motion is in the SO2 since it is a pure rotation. However, end effector pose changes both in translation and orientation parameters. The two key features of the proposed planner are, firstly, if the orientation of the initial and goal locations are kept the same, all intermediate locations will have the same orientation. Please see lemma 1 and the corresponding proof given in the paper. Secondly, if the position vector of the initial and goal locations are kept the same, then all intermediate configurations will have the same position. This fact is presented as lemma 2 in the paper along with the proof. Here is an application of the two key features of the proposed planner. In this example, the robot transfers a glass of liquid and pours it into another container. In this task, neither the position nor the orientation of the end effector remain fixed throughout the path. However, the whole task can be decomposed into two subtasks. In the first subtask, robot moves the glass, keeping its orientation fixed, and in the second subtask, the robot pours the liquid by rotating the glass while keeping the position of the end effector fixed. Notice that the first subtask can be accomplished by the first feature of the planner, and the second subtask can be accomplished by the second feature of the planner. Here we present another key feature of the planner. Given a pair of initial and goal configurations in dual quaternion form, if the relative configurations between the initial and goal configuration pairs are the same, then performing screw linear interpolation independently between the two start and goal pairs preserves the same relative configurations between any intermediate configuration pair. Please see lemma 3 and the respective proof given in the paper. Now I present an application of the third feature of the proposed planner. In this example, we consider a dual-armed manipulation task where the robot has to carry a tray with a glass of liquid from one position to another using both hands. There are two types of constraints that need to be maintained. A. The orientation of the tray should not change during the motion, and B. The relative pose between the hands should not change during the motion. The objective of this exercise is to show that for this dual arm manipulation task, the plan for both the arms can be obtained independently using the proposed planner as long as we perform screw linear interpolation with a common parameter tau for both the hands. The resulting path will implicitly satisfy the two types of constraints at any intermediate point on the path. In summary, we have shown that using screw linear interpolation to compute waypoints of the end effector path allows one to satisfy some common task constraints without explicitly specifying them. We proved that if the start and end poses are in a subgroup, all the intermediate poses will be in the same subgroup. Since planning is done in task space, the planner is insensitive to the number of degrees of freedom of the manipulator as well. Thank you for your time. Should you have any questions or suggestions about this work, please send email to the addresses given here.